Now that we've established the concept of electronegativity and the role that it plays in establishing polar bonds, let's see what this means for larger polyatomic molecules. Our learning goals in this video are to look at the implications of charge distributions of molecules, and then to predict the location where we might find partial charges, that is partial negative or partial positive charges in those molecules. So what is the origin of these charge distributions? Polar bonds basically indicate that the electrons are shifted toward one side or another in a bond, which creates partial charges on the atom. So remember when we looked at hydrogen chloride, there's a partial positive charge on the hydrogen end and a partial negative charge on the chlorine end. So now what if we have a molecule with lots of polar bonds? What does that mean? And how can we visualize that? How can we get an idea of what that means for the molecule? Well, it's going to result in a distribution of partial charges. So we want to be able to predict where those partial charges might be, and for several reasons that I'll enumerate at the end. What we do is we use a device called MEP surface, and this helps us to visualize what this looks like in a polyatomic. Now, MEP stands for molecular electrostatic potential. And the way it's created is we basically form a mathematical model for where the electrons are in a molecule, and then we use that to determine sort of where the electron density is at different places in the molecule. The surface is then created by using a test charge and determining what the strength of the force that charge feels as it approaches different parts of the surface. So it gives us a map basically of where we're likely to find the electrons. This is what it looks like for hydrogen chloride. Okay, you can see it's a very colorful thing. It looks kind of like a 3D shape, and in fact this is a 3D shape. In a program that you'll be introduced to later, you'll be able to look at this and manipulate it in 3D. It shows the approximate size of the electron cloud around the atoms in this molecule, and the colors reflect the relative density. So we know that there's more electron density near the chlorine, so that's what causes it to be shaded red. It's a slightly negative charge on that end. On the other end, a low electron density gives us a blue charge. So we now have a color-coded way of looking at these molecules and determining where they're likely to have both positive and negative partial charges. So can we actually do this without looking at an MEP surface? Well, I'm going to give you a chance to look at MEP surfaces whenever we can, but it's also good to have an idea, an intuition of where one might see this. So for carbon framework molecules, these are the electronegativities that we typically see. Okay, carbon is, of course, the framework for these molecules, so it's sort of the baseline that we want to compare to. And we can see that in the next row, we got fluorine, oxygen, chlorine, nitrogen, and bromine, and all of them have electronegativities that are greater than that of carbon. So we might expect them to draw the electrons to themselves more when they're bonded to carbon. Hydrogen, on the other hand, has electronegativity that's less than carbon, and we've already seen that carbon-hydrogen bond is not particularly polar. It's still classified as a covalent bond, a nonpolar covalent bond. So we're likely to see partial negative charges on the series of elements that are listed in the second row there: fluorine, oxygen, chlorine, nitrogen, and bromine. We could see positive charges on hydrogen, but I want to caution you that these are not strict guidelines. And sometimes we see a partial positive charge on hydrogen, and sometimes we don't. Mostly we see hydrogen as not a particular magnet for either partial negative or positive charges. So here's a couple of examples. In fact, these are two isomers of C2H6O. One of them is ethanol, and one of them is dimethyl ether. Okay, so we can see how they look in these MEP surfaces, and we can also see where the red regions are. Notice that in both of these molecules, the red cloud is near the oxygen. Oxygen is the most electronegative element in these molecules. It draws electrons toward itself, so that's where the electron density is great, and we see a partial negative charge. This is very typical of oxygen in these carbon framework molecules. Now, in ethanol, we also see a partial positive charge on the hydrogen that's attached to oxygen. The electronegativity difference between oxygen and hydrogen is quite large, so there we do see a very polar bond, and the hydrogen is the positive end of that bond. The rest of the ethanol molecule, though, does not appear to have very strong tendency toward either positive or negative charges, and indeed it's a very nonpolar environment away from the oxygen. Dimethyl ether, we don't really see much in the way of positive charges on any of the hydrogens, even though there's a strong negative charge on the oxygen. The positive charge in this molecule that counters that negative charge is sort of spread out over a wide region. Okay, this is also very typical of what we call ethers, which dimethyl ether, of course, is an example. So where would you expect to find partial positive and negative charges on this molecule? I'll invite you to pause for a moment, take a look at this molecule, and think hard about it. I don't think you'll need to think too hard, but go ahead and give it a thought. Okay, this molecule is formic acid, and we can see that it has two oxygens, both of which are very electronegative. So when we look at its MEP surface, we're going to see partial positive charges on the hydrogens, partial negative charges around the two oxygens, like this. That carbon-oxygen double bond is called a carbonyl bond, and it is a particularly well-known polar bond. It's very polar, very strong charge separation between the carbon and the oxygen. So what are the implications? Why do we care about charge distributions in molecules? There are lots of different electromagnetic properties that are determined by these charge distributions. For example, can they absorb light? And we'll see some instances of this during the course of this treatment of electrons and molecules, but this is very important for our study of molecules, that it allows them to absorb light. When they have partial charges, it allows them to interact with other molecules. Remember that electrostatic interactions are the chief means that molecules have for detecting one another and interacting with one another. So having a partial charge basically gives a molecule its identity. It also determines physical properties, such as phase changes. We'll find that molecules that have greater charge separation in them will have greater attractions to one another, and therefore it will drive their boiling points and melting points higher to higher temperatures, because it'll take more energy to remove them from one another. It's also a prelude to chemical changes, and that's really more the topic of the next course. But you should know that when molecules interact, they start with those partial charges, and that leads then ultimately to chemical reactions.